this is a saying. For those of you who don't speak English natively, this is not standard English. It's something that a friend of my grandmother used to say all the time, and it applies here. The point is that your good luck is my bad luck. Your good luck is that most of what I originally was going to say today has been said already by other people, so I have to think of something else to say. And further, your good luck is that I haven't thought of very much, so we'll end a little early, I'm hoping. No, this is really very good, I think, for the math circles movement. I've been doing it for like more than a dozen years, and now other people are doing it and going way beyond things that I thought of, and so I'm glad to take a back seat over there and listen, and so I don't have that much more to add. So rather than what it's listed on that I was going to talk about, I thought I'd talk a little bit about pedagogy and how it relates to math circles. I spent my life as a classroom teacher, not as a mathematician, so I have a slightly different point of view. They start converging. That's a picture of, do you know what that's a picture of? Can you tell?
No.
What was it? I mean, what kind of building is that? Cathedral, right? Or maybe you might say. It's in fact a high school.
Oh.
Okay. And high schools come from a tradition which is based on the university tradition. This could be a university building, right? And university traditions come from clerical traditions. The legacy of high school education is training people for the clergy in the Middle Ages, essentially. This, on the other hand, is an elementary school. Elementary school traditions are very different. Elementary school is a much newer institution. Universal public education was a child of the industrial age, essentially. Not of the Enlightenment, not of the Reformation, certainly not of the Middle Ages. It's much, much newer. My background has been to go from... No, thank you. Keep it up. I'm just going to get messed up with this. In my career, what I did was, I was trained such as it was. I didn't have much training at all as a high school teacher. And midway in my career, I went down and started teaching in elementary school and found this out, and I didn't understand that at all, that there are two different traditions. And it reminds you of the proverb on top. High school teachers, college teachers, know about scholarship and content. Elementary school teachers know about students and pedagogy, much more. And one of the challenges of doing a math circle, especially if you're an academic, or if you remember mostly your high school career, is to look at this and see what do you have to know about kids and students and pedagogy and kids that you might not know. Your strength is going to be scholarship and content. And a lot of what you have to learn is from those things, those other things. And I learned that the hard way. I learned that by going into third grade classes and having kids in tears because they couldn't do things that were very simple, and not being able to predict how they would react to certain things that I was doing. Well, all right. So how do you do that? Well, I'm going to go through some of what I do with elementary school kids, and then we'll talk about how it relates to high school kids. By and large, first of all, in a math circle, and this is one of the things that's been touched on before, you're dealing with kids who are in some way self-selected. The hardest thing is dealing with is in a math circle if I have a kid whose parents force them to go. It's very difficult. But if you have self-selected kids, the kids will be motivated. They won't be smart necessarily. You have to make them smart. But they'll be motivated. And so usually if I have them around a table or something, I put some of this stuff down, they immediately start tinkering without my asking. And so that gives you an in. How do you do these? And some of these lead nowhere except they tinker. There's a general idea that this is a problem. What's the problem? You have to figure out the problem. The problem is to get them apart, to get them together again, and so on. There are some of these that actually generalize one to the other, but that's not what this talk is about. And you've heard enough of that stuff. I go from there typically to more personal type problems. This is a typical personal problem. What I do is put the kid's name in it. Okay, is Harold, can see if you look around the room, but people are generally thrilled at seeing their own name. You know, the sweetest sound, all that. And this group, this is something I started with a group of kids that I saw week by week, and what it grew into was these little plays that I would write, or stories, and some of you have seen them, involving the kids, and you know, it would become a puzzle or a problem and so on, and there would be chains of problems, and you can organize it around that. The point being, I think, for this kind of thing is that the more they do and the less you do, the better they'll learn. And that's my philosophy of this kind of thing. From there, I go to things that don't look like mathematics at all. I was going to bring this for the swap meet. Then I said to myself, it's ridiculous. Everybody has these. This is a Chinese takeout menu. And how can you ask a question here that's mathematical?
Like how many ways can you make it?
Oh, I didn't even think of that. Oh,
That's what I do in my class.
what I asked them is, what's the character for chicken? What's the character for beef? And I just asked them that, and at first they say, how do I do it? And then they realize that, you know, this has got to be beef. It doesn't help if you have all Chinese kids who have taken Chinese class in the morning. But this has to be beef because it occurs every place there is here. Where's the one for tangerine? Well, that's harder. It's 2 characters, and they can figure that out. Even if you can't see it, you get the logical idea. And you just get one of these menus and reproduce it. You have to reproduce it. You have to increase the size because these are generally very small because nobody really reads them. And lately, a lot of Chinese restaurants have stopped putting them in characters. So you can find them. And that kind of thing gets their attention. And I just ask them, and then they figure out. I don't tell them how to figure it out. Somebody will know, and somebody else will. Have you seen this? I talked about it last year. Another source of interesting problems which don't look mathematical is language, and we had a session which I couldn't go to on linguistics because there are wonderful linguistics problems, and this is one that I do with 5th graders. These are 3 English sentences. The first one should have a period after it. Do you see what it says? Well, if you don't see what it says, this is how I show kids what it says. You could have a sentence, champions eat Wheaties, right? And then you could say, have a sentence, champions eat dogs. Generally not true, but maybe it is, you know. And then dogs eat dogs, cannibalistic dogs. And then, but there's also a verb to dog, to follow somebody's footsteps very closely, and I have the kids act it out. And so you can say dogs, dogs, right? And that's a sentence. That's a perfectly well-construed sentence. Well, buffalo is a special case because buffalo is both singular and plural and a verb. So you can start with monkeys love bananas. Maybe buffalo also love bananas. Maybe buffalo love other buffalo. And then buffalo can shove and push buffalo. They buffalo. What are kids getting out of it? Well, this is a notion of structure, which they wouldn't get otherwise. They won't get it in English class.
Is it like that only in English language, or can you make like this in other languages too?
Apparently there's something in German.
In German, you can switch
Flies,
the order
fly,
of
flies.
object and subject on top of this.
Yeah.
But we can recognize it because of the articles usually.
But there's something. There is a sentence like this in German about flies, fly, or something. I don't remember the whole thing, but something. But usually you can't. English is a very flexible language that way. Not only that, but look at the second sentence. Buffalo, whom buffalo, sometimes seen to buffalo still other buffalo. See what it says? And once you do that by recursion, you can make it infinite. If you just Google this sentence, you get a... I'm sorry?
Buffalo, that other buffalo.
Yeah, there's 2 ways to construe it, right? Yeah. You can put the parentheses in different places. And it's not associative.
That's why you need commas.
Huh?
That's why you need commas.
Right, but in fact, commas these are non-restrictive clauses. So.
No, you don't need commas here.
You don't need commas. All right, anyway, if you put this in Google, you get lots more. Linguists go crazy of this, as you can imagine. And there's a lot of things like this, which I'm not...
Buffalo, you buffalo.
Okay. This is another kind of problem that I give also fifth graders. I do it in terms of sushi, but you can do it in terms of anything depending on what the kids are.
Yeah.
3 pieces of U, a piece of A, and a piece of E costs $14. 2 pieces of U, a piece of A, and a piece of E costs $11. This is how I start linear algebra. And then you add them, see? And you do various linear combinations, and you try to pick the numbers so they can't easily guess what the price of 1 is.
These all seem to be USB thumb drives.
I'm sorry?
They all seem to be USB drives.
Oh, I didn't notice that.
Worries
I gotta go find them. There's a street in Tokyo which is all stores of plastic food. It's just unbelievable. All right. This is kinds of things that I just give the kids and they just go. A few more activities. I didn't have time to do this, and I don't think you have time to sit through. But topological maps. What I mean is, there's a book which I failed to bring, but you can do it yourself, which has a map of the United States, but it's a rectangle, and all these states are reduced to polygons, and the game is to tell which polygons refer to which states. It is unique. With little kids, you have to give them a map of a real map of the United States. With bigger kids, sometimes, a lot of times, they know a map. So, and they do it by neighbors or whatever. There's a zinger to this. It turns out the United States is donut shaped, but it's not why you think. What state do you think would give it trouble? Michigan, but it's not the state of Michigan. It's Lake Michigan, because Lake Michigan, if you drain it, there are 4 states bordering Lake Michigan. Either 2 border each other, which shouldn't, or you have 4 in the middle that meet. A point in the middle where all 4 meet. It simply doesn't work. You have to either consider Lake Michigan a state by itself, or carve it up in some unnatural way. But other than that, it works. And then the question is, why does that happen? What's the typology of it? This is what I'm thinking. The less I talk, the more they learn. The less I write, the more they learn. The less I stand, the more they learn. I'm now contradicting what I'm saying because I'm standing and talking to you, but that's a function of where we are now. But particularly with kids, I find this is a good guide. When I was teaching, I used to have kids who had tutors. If I taught in a wealthy district for a while, all the parents wanted kids to learn math, so they would hire tutors, and I was also hired as a tutor. And I would ask, some of the tutors were not very good. They would just do the homework for the kid. And then they have perfect homework, and then the kid would bomb on the test, and I'd be blamed, and so on. So I always told the parents, and I told the kid, if you want to know if the tutor is really doing well, look and see who's holding the pencil. If the kid is holding the pencil, it's more likely that the tutor is doing a good job. If the tutor is holding the pencil, it's less likely. And this is the same kind of thing. And the other thing is that if you compare this with what the Kaplans did earlier today, they did a lot of standing and writing, right? I think that's because of the kind of problem they did. I usually choose slightly different style problems, which are where the structure is delivered to the kids directly. Standing and writing, even though they said that's they're being secretary, does provide structure, and kids need to have a structure. You can't just say, kids, buffalo, 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 what do you think? They have no idea what you're talking about. They need the structure. So it's a question of how you do the structure. What I usually do is I put more structure down on paper so that I can give it to them, and then they do it that way. What I pay for that is the problems are less open than what the Kaplans did, for example. So you have to pick and choose, and do some each time, different things. But this is the kind of thing I wanted to talk about in terms of pedagogy, in terms of the difficulty of getting people who want to run math circles, because the nature of the math circle is usually get a mathematician, some new industry, something like that. And this is the hard part for them, the part where they have to be teachers. I'm almost done. But I did want to say how this relates to bigger kids, high school stuff, because most of my background is working with high school kids, not elementary kids. I'm doing this mostly because I have this experience and other people don't. But they get more formal more quickly. That's one difference. Little kids, it takes a while for the formality to come out. Maybe it doesn't come out for weeks or even years, and maybe that's not the point. High school kids typically are ready for formality more quickly, and middle school, well, it's in the middle. But there's a lot of things you can give them that you just say one thing, and they can work for a year or two, not a year, but a day or two on it. One of my favorite ones is, this is a problem that should be classic, but isn't. We know that if you have two parallel lines, the set of points between them is a line in between, right? And if you have two intersecting lines, it's the perpendicular bisectors, and then you can have a little proof that the perpendicular bisectors of the angles formed by two intersecting lines are themselves not perpendicular. Angle bisectors are perpendicular. What about the set of points equidistant from two skew lines? Don't answer the question. How do you know the answer? How do you know what that shape looks like? Yeah, because you. Yeah, because you probably had it in a math circle way back when. But don't say it. Don't say it. But it's a very interesting question. It's the kind of question kids have trouble with. Another question like that, going from 2 to 3 dimensions is a very rich source of these things. If I have 3 points, boom, 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 on a plane, how many parallelograms can I draw with these 3 points as vertices? Well, that's not hard. There's 3. There's one up there, there's one over there, there's one over there. Should I do it on the board? Yes. 3 points, any 3 points, they're not collinear. There's one over here that makes a parallelogram, right? There's one over here that makes a parallelogram, and there's one over here that makes a parallelogram.
But it's a beautiful, beautiful diagram.
It is, not when I draw it.
Yeah.
But all right, it comes out very nice. But then you ask the same question in 3 dimensions. You have 4 points that form a tetrahedron that are not coplanar. How many parallelepipeds are there with those 4 points as vertices? Much harder problem. And I'll just leave. Much harder problem.
What is given is when we need to add.
See, he's starting already. That's what happens with kids. That's what you can. You see, you don't have to give them any structure to do that. As long as they know what a parallelepiped is, sort of a crooked box, then they can do it. Here's a problem that I use all the time, and this is classic. I'll show you where you can get it, where you can see it. I have 4 points on a plane. Draw a square whose sides go through all 4 points. One of whose sides go through all 4 points. And I just didn't do it. This is a rectangle. But if you have 4 points in a plane, draw 4 lines that form a square, 1 through each point. Can this be done? Well, almost always, except when 3 of them are collinear. And it can be done in usually a total of 12 different ways.
Wow.
And after they solve that, they can go use Geometer Sketchpad or something and try to construct all 12 ways. A generalization of this, since everybody's hawking books, I'll hawk mine. This is Hadamard's geometry. Hadamard's elementary geometry is a wonderful source of problems. Some of you know it from the old country.
Translate the second volume too.
Well, sorry?
I hope you'll translate the second volume too.
I should live so long. I translated this, and it now appears in English. And I also half translated and half compiled a set of solutions to problems. This appears in that problem, together with things you can do in the classroom and extensions and so on. Hadamard points out the extension to this, which is, so this is a square. A square is a type of quadrilateral, and what you're doing when you say find a square which has this property is you're determining the shape of the quadrilateral. So suppose you have these four points, and the generalization is draw lines, 1 line through each of the 4 points, such that their intersection forms a quadrilateral similar to a given quadrilateral. turns out to generalize very nicely if you do it the right way. But and then there's several other extensions. But this is the kind of thing. You see how this is different from this problem we started with, Zvezda's problem. Zvezda's problem is more on the Olympiad level. This is, I just said it to you without, and you'll remember it if you care to. So it's the kind of thing that draws them in. Not only that, but there are a lot of things that you do with elementary school kids you can do with high school kids, and it has a different meaning. You can easily see that you could go very far with maps, topological maps. You know, is it unique? How do you do? You know, what's the dual? All kinds of things that you can do about that. The sushi problems with the flash drives end up being vector spaces, of course, and linear dependence of vectors in a very natural way. They just do it. And you can actually go from that to solution of simultaneous equations more easily than the other way around. But it depends on what textbook you're using, if you're using a regular textbook and so on. You know all about magic squares, right? We were talking about magic squares, you know.
We don't know all of them.
We know what they are, but we don't know
That's all
what
right. So with little kids, I did this upstairs on Saturday. It's a very nice thing to give them cards. What's this? To give them cards and have them derive that magic square. And the way they do it is, the way I do it with them is, just give them so that the rows are all the same. And they can do that pretty easily. And then that the columns are the same, and they can do that by swapping around and making them even. And then the diagonals, you have to swap whole columns or whole rows. That takes a little while, but they do get it. They get more than one of them, and as was mentioned earlier, you can derive from that symmetries of a square. But do you also know that you can derive vector spaces from this? I asked them to do. All right, so this is the cards 1 through 9. So far, I did it up to. I did the following upstairs. Make a magic square of cards 2 through 10. I use playing cards, and of course, you don't need a full deck to do this. You just take all the decks of cards that people have discarded because pieces are missing. And it takes a little while. The first time they do it, this happened beautifully upstairs on Saturday. They took the cards with 2 through 10, they started shuffling them again and putting them around, and then I showed them that you can just add 1. And they all were flabbergasted, suitably flabbergasted. Right? If you just add 1, the magic property remains. And then you can ask them about the numbers.
How old were those?
Sorry?
How old were those?
I sat next to a little 7-year-old who got the original.
Yeah. And this is a little harder, but next year he'll get it. Make a magic square with the multiples of 3 up to 27. Well, once they've seen this, they can do this. You multiply this by 3. Well, what does that mean? Drop the condition that the values of the magic square have to be different. Just keep the condition that the sums have to be the same. Well, then this is a magic square, right? The sum is always 3. Trivial. It's a constant magic square. The point is that you can see the green one as having added the original one to this one term by term. And if you think about it for a minute, if you have 2 magic squares in that sense and add them, the sum will be magic. And thinking about this, if you have a magic square and scale it by a factor, the new square will be magic. Well, that means magic squares are objects that you can add and scale. What do you call those objects? Vectors. And then you can begin to ask all the standard questions about vector spaces. What is its dimension? What is its basis? And so on. And it gets pretty far. I'm not sure. Yeah, we did that the other day on the table here. I'm not sure, and this is where I'd like to articulate with mathematicians, can you really get meaningful theorems out of this? Or is it just an exercise? I don't know. There's a few more things I haven't told you, but I don't know. I think there's more to that. Do you know the game Giotto?
No.
I don't know. Do you want to, I'm about to end. Do you want to play a game or do you want to end? This is a game, John. And you'll see, I think it's more effective when I tell you why. You'll see why I do it. And it'll be much more effective. All right. Did anybody see what I wrote there?
Yes.
Too late.
Oh, too late. All right, then never mind. I won't write it. I have a word in my head. It's a 5-letter word in English. Yeah, the dramatic thing is to open it up later at the end.
No.
Okay.
You won't be able to
Big letters.
You can
All right.
slide
They're
the.
cheating.
All right, I have a 5-letter word back there. No 2 letters are the same. You can play this with 2 letters are the same. It's a significantly harder game. You have to guess my word. The way you guess my word is you give me another 5-letter word, and I will tell you how many letters they have in common. Not where they have, just how many.
Slide.
Huh?
Slide.
Slide.
I think that's
One letter in common.
Slide.
But do you also say which letters are in the proper place or no?
That's too easy.
What's too easy? It's not easy at all.
No, it's not easy, and it's not doesn't make it easy for little kids because they won't keep track of it. But this they'll keep track of down to 3rd and 4th grade.
Phyla.
Phyla.
Down to kindergarten, we did it.
One. By the way, your words, your test words, do not have to could have double letters. Let's hear.
Rome's.
Hmm?
Rome's.
Rome's, R-O-A-M-S. Two.
Tests.
Tests. Okay, thank you. That's what I want to make. There are 2 S's here, right? My word can have 0 S's or 1 S, but it can't have 2 S's. So in fact, it's 2. If S is in my word, it would only count as one of these. Okay, that's how it works. If there are 2 S's, then you do it differently, but there aren't. That's what makes the game harder. So this, in other words, this would be the same score, but I don't allow 4-letter words. This is very bad because she just guessed my word. All right, but you see, but I think this is that's all right. This is. But you see, the point is that I can play this with 10-year-olds. I can play this with 60-year-olds. It's still a good game, and it's still intriguing. And what they get out of this is the nature of a logical argument. There, people are talking about proof. You know, when do you introduce proof? I don't think anybody really knows when it's best to introduce proof. It's something that's not well worked out in the research literature. What does it mean to go from reasoning generally in elementary school? The first thing is inductive reasoning, making and stating generalizations. How do you go from that to deduction? I'm not sure I know. But this is a genuine example of deduction. You're making deductions as you do this, and kids naturally do that.
But really young children can play checkers and mastermind and these kinds of
Yeah, there's mastermind is like this, right?
It is.
But I like this one better.
Sure. But they can play these kinds of games and use deductive reasoning. 5-year-olds can.
Yeah.
4-year-olds.
Yeah, right.
Well, you do it with numbers 1, 2, 3 if you're doing it with the real little kids instead of the full alphabet.
Yeah, there are all kinds of things you can do. I like doing this with 10 and 11-year-olds just because they don't see it as mathematics, and I feel like I'm pulling one over on them. But that's my personality. Yes. It was marketed in the 1950s as a game spelled like this, and I just altered the spelling because I felt like it. Yes, I know, so was I. But it was marketed like this, and they sold these things. It's very useful, and if you're playing with kids, it's very useful to put an alphabet down, and as you eliminate letters, you cross out the alphabet. So they marketed a pad with the alphabet and a place for the secret word and so on. You don't need nothing.
You can only eliminate
Will someone explain what else?
Okay, well,
You can certainly eliminate letters with 0. 0 is great
Yes.
to get a word with 0. But if somebody had, now this is not true,
okay.
but if you go for, in fact it is true here. Glide has 2. Well then you know that G is a letter,
Yes, sure.
right?
And S is not.
And S is not. And in fact, I showed somebody this. The score for roams is the score for slide. You can do this. These scores are equal, therefore these scores are equal. That's the only one. All right. In other words, there are 2 letters in Rome. This is not true, is it? Phyla. All right, slide and phyla. No. Roams and glide. This value is 2, right? Well, forget about that value, but you can cross out, I'm not having any success here.
That's what I'm saying.
You can cross out common letters, and the sets of letters remaining have the same score. They don't not 2, because you might be crossing out letters that are there, but they have the same score, and you can work with that. Essentially, these are 26 variables having the value 0 and 1.
Yeah, like you can only ask 26 questions, like 5 times A, 5 times B, and they will end up.
Yeah. You could write, let's put it so, you can write a computer program that does this. I think you could.
Yeah.
But it's fun to do. Anyway, that's all I have to say.